Last class we extended our language with lambda functions, and with lambda functions we've actually made quite a big change to our language. Um, we've really made it so that at this point there's going to be very few things that we're going to have to add to the language itself. Most things we'll be able to have just as part of the desugarer. And what I'd like to do um, at this point is take a little step aside from developing the language and sort of go back to some first principles and talk about um, the underlying theory that we're using, which is called the Lambda Calculus. The Lambda Calculus. Now, the Lambda Calculus was developed by Alonzo Church in the 1930s. And it's really the underpinning of pretty much all programming languages today. Church was Alan Turing's advisor, and if you have taken Foundations of Computer Science, when we say the Church-Turing thesis, he's the Church part of it. Now, the idea of the Lambda Calculus is that we want to define a minimal logic for writing down computations, and it is really quite minimal. Here's the entire extent of the Lambda Calculus. We have expressions, which are either values, variables, or applications with exactly one argument. Values are lambdas with exactly one argument in a body. Evaluation contexts are a whole, or there's an e on the left and an expression on the right, or there's a value on the left and an evaluation context on the right. This basically says that we evaluate from left to right. And that there's one rule, and that one rule says that if you're in a context and you see a lambda x dot e applied to some value v, and that's the same, that reduces to that same context where we take the expression e, we go inside of it and we find all the x's and we replace them with v. So this 4-line little block is the entire Lambda Calculus. Now it turns out that all of the things that we've done so far can actually be represented inside of the Lambda Calculus. Now you may say to yourself, that seems strange because our language is so much bigger, right? Our language has, I think we're on J3, I'm not really sure. Yeah, I think we're on J3. Our language J3 has if statements, it has bools, it has numbers, it has operations like plus and subtract and so on. And it has multi-arity functions. Okay, so it's got all these different things. Now the thing that's remarkable about the Lambda Calculus is that it actually contains all of these features. Let's look at a little example. So for instance, notice that it only has one argument. We can actually simulate multiple arguments with a single argument. Suppose that you wanted to have a function that took two arguments and added them together. So in J3, we could write that in the following way. We would write lambda xy and then plus xy. Then you could call this function, here let me put it in parentheses, then we could call this function by writing something like 2, 3. Now once we did that, the 2 would flow into the x position, the 3 would flow into the y position, and then they would pop out over here, and we would get plus 2, 3. And that would take one step to do that substitution. In the Lambda Calculus, however, by the way, we write the Lambda Calculus with a capital L sometimes, a capital lambda, which is like a triangle. So in the Lambda Calculus, we can write the same expression in the following way. We can write lambda x, lambda y, and then we can write, let's just imagine we have a function called plus. We'll talk about that in a moment, how to do that. Plus xy. And plus, of course, it takes one argument, so we first call it like this, and then we call it like that. Now we would call this with 2, and then 3. Now the thing is that what will happen is that this 2 will go into that spot, and then we will get lambda y plus 2 y, and then that will be called with 3. So notice that this new lambda right here remembers what the first argument was. This is called currying. Currying. And is named after this guy, Haskell B. Curry, who was an early researcher on the lambda calculus. And so currying is the observation that unary functions, like the lambda calculus has, allow us to simulate multi-arity functions. Now, what about these other things like ifs, booleans, numbers, and addition and whatnot? Well, it turns out that the lambda calculus contains these as well, although it contains them after a bit of, what's the right word for this? After a bit of encoding and understanding what booleans and numbers really are. So let's talk about what booleans really are. So what are bools really? All right. Now, the key thing to realize about a bool is that a bool just sitting by itself in memory somewhere, you may think to yourself, okay, well, what's a bool? Well, true is 1 and false is 0, and that's what a bool is. The thing is that merely thinking about what the representation of a boolean is fails to recognize that a boolean that you never observe never makes any difference in your program. So what we want to do when we want to think about what a data type really is, we want to think about what operations it has. Now, what operations it has are, of course, an if statement. The thing that defines a boolean is that you can take it later and include it as part of an if. So what we would say is that there's a system of equations that determines what the bools are, and it shows the relationship between the booleans and if. Gotta pause for 1 second. Someone was sneaking in. All right. So there's a system of equations that determines the relationship between true, false, and if. And there's 2 equations. We say that if true a b equals a, and if false a b equals b. So any values for true, false, and if that satisfy these equations are a valid model of Booleans. And it's actually quite straightforward to do this inside of the lambda calculus. Essentially what an if does is it uses the true and false to select between options A and B. So what we'll do is we'll write down an if in the following way. We'll write down lambda c, that's the condition. Lambda t, that's the false branch, sorry, that's the true branch. Lambda f, that's the false branch. And then what we're going to do is we need to use c to select them. But what we'll do is we'll actually just make it so that lambda c, the c right here, the c argument, we'll just get sent those arguments so it can decide it themselves. So it will just call that with c, t, and f. In other words, it turns out that if is really just the identity function because it just takes the condition and then just returns it, and then the condition will then be applied with other things. All right, now what are the conditions? Well, true needs to take a true branch and a false branch, and false needs to take a true branch and a false branch. But what true does is it returns the true branch, and what false does is it returns the false branch. So these 3 values right here fully implement true and false. Now, you may think to yourself, well, this is weird. I mean, these are functions. Like, there are other operations that have to take place that you have to use true and false for, like maybe not. Well, not is just another system of equations. So not true is supposed to be false, and not false is supposed to be true. Okay. In other words, these formulas are reversed. If we do if not true, we should get b. Well, we can write not in the lambda calculus as well. So it's going to take a condition, it's going to take a true, it's going to take a false, but then what we're going to do is we're going to call the condition with them in the opposite order. we'll send in the false and then the true. Now, if the condition is true, it's going to return the false side, and if it's false, it's going to return the true side. So now we have an implementation of not. What we're really doing right here is we're doing object-oriented programming. Object-oriented programming. Now, you may have been falsely taught that object-oriented programming is about writing down classes, where the classes store their fields privately from other things, and they expose them through getters and setters. This is a cargo cult understanding of what object-oriented programming is. Object-oriented programming is really about hiding the representation of things from their users, meaning that they are only exposing a consistent interface. So in this case, we are doing an object-oriented encoding of Booleans, where the thing that Booleans can do, their interface, is simply like a choose operation, where you send in two values and they choose one of them. And that is the only thing about a Boolean that's revealed, the way that it chooses things. There's no way to inspect what its internal representation is. Therefore, we can represent it by something like a function. All right, well, let's play the same game, but now let's play it with numbers. So what is the thing that a number is? So what is a number? In other words, how can we do an object-oriented encoding of a number? Well, the thing that defines numbers is that they represent, like they can be used in like for loops, for instance. They can repeatedly do something. So for instance, 0 would be a function that doesn't do anything. And 1 would be something that does it once. Whereas 2 would do it twice, for instance. Okay. So if that's the way to think about what they are, that they encode the idea that you can do something multiple times, that basically tells us that they need to be functions that first accept the thing that they're supposed to do. We'll call that argument f. So they have to take an argument, which is the thing that they're supposed to do. Now the next thing is that they have to take, the only way to call a function inside of the Lambda calculus is to give it an argument. So what we could do is we could just say that they have some default argument, like they always call it with some particular thing. But that's obviously restrictive. What we would like is make it so that they can be called with whatever the user decided. So we'll take another argument, which will be the argument that the function will be called with. So now 0 won't call the function at all, so it'll just return its argument. Whereas 1 will call it one time, and 2 will call it twice. So this right here is a consistent way to think about what a number is. What a number is an operation that's like, well, sorry, it's like something that's going to be applied in the future. Now, from this definition, we can build a library of functions that operate on these things. For instance, we could write the add1 function. Add1 meaning that it takes a number and returns one more. So what does add1 do? Well, add1 takes a number, n, and it returns a number. Well, numbers are things that take an f and then take an x. Okay, so now it's a number. But this number should be one more than the number n, which means that it should call the function f one more. So it's going to call the function f on the result of calling n with f and x. So now when we call n with f and x, it's going to do it, say, 4 times, and then we're going to do it one more time, thus making 5. So let's walk through running add1 on 1. So if we run add1 on 1, then add1 is going to return lambda f, lambda x, okay? And then that 1 is going to go into n, and so we have the f from the add1. Then we're going to have 1 fx. Well, now 1 fx is just going to call that, so that means that we're going to call 1 with f and x, so we're going to get lambda f, lambda x, f, fx, which it turns out is exactly the same as 2. So add 1, 1 equals 2. Okay? So add 1 definitely does the right job. Well, we can build other functions as well. For instance, we can write the add function. So let's work through it. So add is going to take a number n, it's going to take a number m, and it's going to return a number. Numbers take a function and a value to call the function on. Now what it's going to do is it has to call the function f as many times as m does. So we can write that as m f x. Then it has to call the function as many times as n does. Well, clearly it's going to do that by calling n and calling it with f. And now mfx is going to be the argument that goes in, so that means that's going to be returned if n were 0. And if n wasn't 0, we would call f one more time on that. What about a function like 0 question mark? Something that is a way to determine if a number is in fact 0. How can we write that? Well, what we would do is we would write a function that takes in a number. Then we want to call that number. And what we would like to do is make it so that if the function's ever called, then it will return false, because it's not 0. But otherwise, it returns true. Okay? What about a function like multiply? Well, multiply takes n, takes m, returns a number. All right? Now, what do we want to do? What we want to do is you want to make it so that every time n calls the function, it actually calls it m times. So we could do that by writing it n mf x. Now, if n is 0, then it's going to call the function 0 times. And if n is 1, it's going to call it mf times, which is, of course, m times. And if n were 2, it would call it, like let's imagine it were 2. Then we would get mf x. So that means, now let's imagine that m were 3. Okay? Well, this right here would be equal to f 3 times x. And then that would go into here, which would get another f 3 times f, which is, of course, equal to f6, which means that 2 times 3 is 6, which is right. Okay? So multiply definitely does its job. Okay. So we've done Booleans, we've done numbers. What about things like data structures? What about the idea of a data structure like a pair? So like a Cartesian pair. Well, again, we have a system of equations. So the system of equations says that the first thing in a pair of A and B would be A, but the second thing in a pair of A and B would be B. Okay? So we're going to have to come up with a definition of pair, a definition of first, and a definition of second. Well, first and second are both going to take as arguments pairs. And pair is going to take as one argument the left thing and one argument the right thing. Okay, now how are we going to relate these together? Well, it's actually quite easy, because basically what a pair does is it's going to remember the two arguments, which it's going to do inside of this closure, and then wait for first and second to say which one it wants. So that means that we're going to wait for a selection. And then we're just going to give the selection the left and the right. And by giving it the left and the right, now it has the opportunity to decide between them. Okay, so that means that what first is going to do is it's going to call the pair and give it one selection, and second is going to call it and give it a different selection. Now how do we select? We of course say true and false, because we already know that true and false are functions that select between different options. Once we have pairs, we can write a very useful function which was called subtract1. So what subtract1 is going to do is it's going to take a number and it's going to return one number smaller. Now that's kind of a weird way that selection works. Sorry, a weird way that subtract1 works. Which is that basically we need to do something n times and end up with n minus 1. So that's a little bit strange. Here's the idea. What we're going to do is we're going to call the function n, the number n, and as an argument, it's going to take a pair. And what it's going to return is a pair of the second thing inside of that pair, and then add 1 of the second thing inside of the pair. So what it's going to do is it's going to return the old value plus 1 more, and we're going to start off with 2 zeros. What this is then going to do is it's going to make it so that at the end we're going to get a pair where the left thing, the first thing, is 1 less than the right thing. So then we'll return whatever the first thing is. And notice that because that starts off as 0, that means that if you subtract 1 from 0, you get 0, because we're not going to represent negative numbers. Alternatively, we could represent subtract 1 by doing something like, by making integers. But this is really subtract 1 on naturals. Okay, so at this point, we've got add 1, subtract 1 is something 0, we have multiply. Now would be a great time to write a function like factorial. So how does factorial work? Well, factorial is going to take in a number, and then it's going to say if that number is 0, then what we're going to do is we're going to return 1. i.e., we're going to return the add 1 of 0. Okay? Then what we're going to do is we're going to call, otherwise, we're going to call multiply of n and the factorial of subtract 1 of n. Okay? Now there's a few little tweaks that we need to make with this. First of all, notice that because it's the lambda calculus, we've got to call this like that. Okay? Because we've got to call mult n and then pass in fact sub 1n. The next thing is that what if does is it selects between two options, but we want to select between two functions because we don't want to actually run this all the time. So what we'll do is we'll wrap this in a lambda x, and we'll wrap this in a lambda x. And then that will now select between the options. And then once we select between those options, then we'll call it. And let's just call it with 0, just something that will get ignored. Because that x right there is the thing that's going to be ignored. All right, so now that we've, and then I guess one more thing is that we need to change the if, so it takes this as an argument. Then we need to add a parenthesis right there, and then we're good. Okay, so now we've converted factorial into the lambda calculus. Unfortunately, there's a problem, which is that this thing right here, fac, is unbound. Because right here when we write factorial colon equals, we're saying that factorial is defined as this lambda calculus term. So that means that this fac right here is an unbound variable. The only way to bind variables is to have them as part of the lambda. So we could add that right here by having lambda fac. But now this wouldn't be the factorial function, it would be the make factorial function. Because if you gave it the factorial function, it would return the factorial function. But of course, how can we figure out the factorial function to pass in? Again, we have a system of equations. What we would like is a solution to the following function, to the following thing. We want to figure out the real factorial function, which we'll call rfac, the real factorial function. And we want that to be equal to calling make factorial on the real factorial function. This is what's called a fixed point, because we would like to have a value x that when we send into a function f, we get back the same thing. We start with x, we send it into f, and we get back x. Now, remarkably, there is a way to discover the fixed point of any lambda. And it works like this. There's a function called z, and it looks like this. It says lambda f, lambda x, f applied to lambda v, x applied to x, applied to v. That closes that parenthesis, this closes that parenthesis. And then we're going to call this function with another thing, lambda x, f, lambda v, x, x, v. Now, why does this work? Well, let's see it actually work. So, imagine we're going to call z with some argument capital F. Well, that means that this f right here becomes the big F. So we would get lambda x big F lambda v x x v. And then that would be applied, notice that this is an application, to lambda x big F lambda v x x v. Okay, well now that's an application, so that means that this function right here gets sent in to that x, and then it will go into there. So that means that we're going to end up with an f on the outside, and then we're going to get lambda v, that's that v, and then we're going to get this term right here, which is lambda x f lambda v x x v, and then that is going to be applied to lambda x f lambda v x x v, and then this is all applied to v. Okay, well notice that this term right here, this one in the middle, is the same thing that we started with, so therefore this is equal to f of lambda v zf called with v. In other words, zf is equal to f applied to that, because notice that this thing right here is basically the same, I'm going to write squiggles, is basically the same as f of zf. It just has an extra lambda v there. So notice that when you call f with zf, you get back zf. Therefore, zf is the fixed point of this function f. In other words, if we write down, we then would know that factorial is equal to calling make factorial, to calling z with make factorial. So if you call z with make factorial, it will return a factorial function. So notice that this now shows us that the lambda calculus includes pairs for subtract 1, it includes Booleans, it includes numbers, it includes recursion, it includes all of the different things that we might want inside of a programming language. Now, of course, it does it very inefficiently. One thing to note is that it uses like its what's the right way to say this? Its numbers are unary encoding of numbers because 1 is 1 more than 0 and 2 is 1 more than 1. It would be possible but more complicated to define a binary encoding inside of Lambda Calculus, but it's not really important to do that because we don't really ever use this directly. Instead, what we do is um, um, the fact that Lambda Calculus includes all these things is really just a theoretical tool to help us realize that when we add new things to languages, we're not fundamentally changing what they can do, we're just making it more convenient to use. All right, so that's enough for today.